Um, Hi everyone. So in this video, we will talk about the residual analysis and the model diagnostics for multiple linear regression. So, well, we said that the original model for a linear regression is something like this. So beta 0 plus beta 1 x1 plus, let me just write this as yi, x, let's say x1 I, beta 2 x2 I plus epsilon. And well, the thing is that we assume epsilon I is normally distributed with zero mean and variance sigma. But the thing is that we never observe epsilon I. So what we observe is, so we just estimate beta 0 as B0, beta 1 as B1, right? I, and beta 2 as B2, and then we have the error term EI. So the error term EI mimics the random terms epsilon i's. And what we do is we just plot them and we just analyze them, in fact, by plotting them to see whether this assumption is correct or not. Okay. So we remember that epsilon EI, the errors, is the difference between the real value and the predicted value. Okay, so the predicted values in matrix notation can be written like this. So remember, our B was X transpose X inverse, right? Minus X transpose. So remember, in matrix notation, I have Y is equal to X times beta. So instead of beta, I'm just using this. So we have X times B, which is also equal to X times what? X transpose X inverse, right? Times X transpose, right? Times and so this is X times beta instead of beta. And so I have a Y here, sorry. So B is equal to X transpose X inverse, X transpose times Y. So I have a Y here. Okay, that's what we have, right? So this is equal to Y hat, right? XB is equal to Y hat. So Y hat is equal to this thing, right? So this is also called H matrix or hat matrix because it just produces the hat values when you just multiply it with Y, right? And what is Y hat? Y hat is the vector. At each element, you have Y1, Y2, you have Yn for n observation. This is Y hat. So Y1, Y hat 1, Y hat 2, and so on and so forth. Okay, so this is hat matrix and so on and so forth. Well, the residual terms, well, they are not independent of each other, right? The EIs. In fact, the variance of the residuals are given by 1 minus HII times sigma square, right? So these are the variances of EIs. The variance of EI is equal to sigma square, right, times 1 minus HII. Where HII is, so we said that I have the hat matrix. So HII is the diagonals of this hat matrix. Right? Great. So in fact, many statistical packages produces what we call as the studentized residuals. Okay, the studentized residuals, or well, sometimes they are also called the standardized residuals. Okay, the standardized residuals. So the standardized residuals is equal to EI divided by S times 1 minus HII, right? So remember in the previous slide we said that the variance of EI, so sigma square of EI is equal to 1 minus HII times sigma square. Hence, the variance of EI is equal to in square root 1 HII times sigma, right? Since we don't have sigma, we will put the estimate there, okay, which is S here. So in fact, this is what? This is the estimate of the standard deviation of what? This is the estimate for sigma of the error, okay? And this is EI. In fact, this EI minus 0, right? Because this is the expected value of this EI, right? So EI minus its expected value divided by its standard deviation. So what we expect to see here is that, well, this is a sort of a T distribution, right? This is a sort of a T distribution. So the student-sized residuals look like a T-like statistic, which provides a standardized unitless measure of the size of the residue. Okay, so when you just plot the residuals, well, you see something, but since they are not standardized, well, you don't know what should be. So their expected value should be 0, but you cannot know what should be their size. Okay, so this student-sized residuals just give you a sort of a standard observation, standard sort of looking at the values of the residuals. Another set of studentized type of residues are called R-student values. It's pretty much the same. What you do is you just divide EIs, okay, EI, their terms by what? By the estimate for the standard deviation, but now the estimate for the standard deviation is a bit different. So this is the estimate found by, okay, by just deleting the ith data point. Okay, so if you have, for example, in the next example, we will have 17 data points. So, for example, S minus 3 is the estimation for the error term where you delete the third point and find the estimate using 16 data points. Okay? So this is to reduce to effect of the ith residue on the standard deviation. So under the condition that the expected values of the epsilon i's are equal to 0, okay, well, this Ti is in fact the value of a random variable following n minus k minus 2 degrees of freedom. Okay, so that's great. So this is T random variable with what where v is equal to n minus k minus 2 degrees of freedom. Okay, given that the expected value of epsilon I that's equal to 0, right? Well, while plots of the raw residuals, which is the unstandardized ones, well, they can be helpful, but it is many times, often, it's more informative to plot the studentized or the R-student residuals. Okay? Well, there are three types of violations of assumptions that can be detected through the use of the residuals or the residual plots. First, well, the presence of outliers. Well, what's an outlier? We will see them in detail in the next slide. And it's a sort of extreme observation. Okay? Second, we can just check the heterogeneous error of variance. Okay, heterogeneous. What we expect to see homogeneous values, right? And the third one is the wrong model choice. So if we need some kind of a transformation. So what's an outlier? Well, outlier is an observation that is too far from the rest of the data points. Okay, so that's an outlier. That's out of the rest of the data. So an observation will be an outlier if the expected value of its residue, okay, its residue is not 0, right? So an outlier may also adversely affect the fitted model and thus cause the other residues to be too large. And also it just affects the prediction ability of the linear regression model. So as we said, the R student residuals, the TIs should be centered at 0, and they just range roughly from -2 to 2 because, well, since its degrees of freedom just changes, well, it's roughly should be between -2 and 2. Okay? So too large or too small values, or well, indicate potential outliers. So if it is, for example, plus 10 or something like that, or -9 or something like that, then they are potentially outliers. So if we have a good reason to believe that a data point is an outlier, we may drop it from the analysis and refit the model. Okay, so you should have ambiguity, or you should have a reason to believe that that's an outlier. Then you may drop it. Okay, it depends on the context. If you are sure that, well, that observation is perfectly correct, then you should not remove it as well. Right? But if you think that there is a problem with the observation, with the experiments, then you may just drop it from the analysis. Well, this should be not an automatic decision. So if this is an outlier, just remove it. Well, it's not an automatic decision. It should not be an automatic decision. It must be taken with great care. Okay, so we just don't use the residual clause to perform a formal hypothesis for outliers. That is, we don't say that, well, this is t-distribution with n minus k minus 2 degrees of freedom. So if it is above a threshold, then just reject it to reject and the hypothesis which say that it's expected that is equal to 0, right? But, well, it just gives the plot of the student as or our student residuals just gives us, the plot gives us a very important, let's say, information regarding the outliers. So here we have an example. Well, in a biological experiment, the relation between two grasshopper catching methods is analyzed. Okay. Well, the response variable is y, which is one of the catching methods, which is drop net. Okay, so what they do is they just put a kind of a trap, okay, a trap which is made of nets, okay, and that trap they are just catching the grasshoppers. And there are two regressor variables. The first regressor variable is the other method, which is the sweep net method. Okay, so they have a kind of a tool which they use to just catch the grasshoppers. And the second one is the average plant height in the field. Right? So there are data for 17 experimental, let's say, runs. And here we have, so this is a sweep net. Okay, so what they do is they just use this thing, this item, right, to just catch the grasshoppers. And for example, there are some grasses here, there are some plants here. So the height of this plant is another. So this is x2, right? And x1 is the number of grasshoppers caught by this sweep net. And the first one, y, is the drop net, which is you just put some kind of a, let's say, some kind of a trap like this, okay? And that should be very nice. I know it. Great. Good. So a trap like this, you just put it into the let's say into the field and wait the grasshoppers to be caught in this net, right? And what you're trying to do is, well, this you try to find, you're trying to see whether there is a relation between this sweep net and the let's say this deep net, drop net. Okay, so and you're trying to estimate the number of let's say grasshoppers caught by the sweep net. Okay, if you just use sweep net, what should be the number of grasshoppers caught by the let's say drop net? And another thing again, and in the other variable is the height of the plant. Okay. Well, that's what we have. There are 71 observations. Well, it turns out that, well, you are able to, so these are the average numbers, okay? So that's why, because you cannot have 4.15 grasshoppers, something like this. So you just count this many grasshoppers, okay, and the plant height was 52 centimeters. And it turns out that there, in that field, on the average, you just count 18 grasshoppers using drop, okay? And it turns out that, well, they feel there's a problem in the fourth data point. Okay? Right. The model to be fit is, of course, you have beta 0 plus beta 1 x1 and beta 2 x2. And as we said, there's a problem with the fourth data point. So you think that it can be erroneous. So this is your fitted model, okay? So if you just put the data into R or Excel, this is the data that you have, B1, B0, B1, and B2. And the fitted model statistics are, well, R squared is 0.92 and S squared is 5.58. So R squared, which is 92.44%, that's a pretty high thing. And the residuals, the data for the residuals are given as follows. So these are the original values, right? These are the y hat values. This is the difference, which is the error term. So just look at this error term. So the other error terms are in the magnitude of, at the magnitude of at most minus what? Minus 2.28, right? So this is the largest, let's say, residual, but this residual is just threefold of this largest. So this is the HII. Remember what was HII? I'm not sure, but X transpose X. So this was Y. Let me Y, right? So this was B matrix. I guess this was something like this, right? X transpose X times, is it? So I'm not sure. Let's go back. Let's go back. Okay. So what was the hate matrix? Let's remember that. So the hate matrix, okay. So it was X times X transpose X inverse times X transpose, right? X transpose X inverse, X here, and X transpose here, right? And okay. So this is the, so what, let me just clear this. So this is, no, let me just take the eraser from here. Right. So I have again X times X transpose X inverse times X. So, okay. This is X transpose, I guess. Okay, these are the diagonal values, and this is S times 1 minus HII, and this is the, so this is the R student value, right? And this is the studentized residues, right? So just look at here, just look at here. Well, this R value is larger than 2, okay? And this one is fairly larger than 2. So this is almost 10 and this is 3.5. Well, this just shows you that there's really a problem with 4. So if you have if the experimenter feels that there's a problem, there can be a problem with the fourth experiment and I should check it, then it means that, well, okay, there's a problem with this one. So what you should do is just remove this data point and just make the, then just remake the regression, okay? Okay. So if you just plot the studentized residues with the predict values of R, as you see, well, these are the residues, okay? So these are the residues, the studentized residues, and this is your outlier. Okay? So this is a perfect outlier. And since the, as I said before, since the researchers think that there should be a problem, there can be a problem with this observation, we just validate that, well, there is really a problem with this data point, guys, and we said that, well, that's an outlier, hence we can just remove it from the model and just rerun the model. Okay, okay. So since one of the basic, another check is, one of the basic model assumptions is that the normality of the error terms, we should also draw a normal probability plot of this studentized residues to see if there is any significant deviation from the normality. Okay, and okay, and this is the normal plot of the standardized residues. Okay? And you see that, well, this 4, this is the 4th point. Well, as you see, this is 3.5, which is, this is these are the studentized residues, okay, studentized residues, right? Well, it turns out that, well, this is far away from the normal plot, which means that, okay, this is really a problem for the model, and hence we can just remove it. Okay?